Okay, so let's continue with the last lecture of Drª Cristina Chiappini. Okay, Cristina.
É a última aula da escola também, né? É. Okay. So here we are to the next lecture. First, I apologize for the switch with Rafaela, and I'm very thankful for her, so that I could prepare my lecture a bit better, because yesterday we had many other things coming up. So we are here in our fourth lecture. Remind you, we went through the galaxy quite a lot, and this lecture was about continuing about the bulge and the future. Okay, I think I have in the lectures mostly of what I wanted to talk about. There is one piece that I haven't included, two pieces which are not part of this school but are important that I just want to say. One is about the halo, and I will briefly touch that, but it's not the goal of the lecture to go into the halo and talk about the streams and all that, but I will put some reference, because if you work on the area, keep an eye there. And the other thing is about really like hardcore chemistry, where you use TSNE and other things to disentangle stellar populations, especially for surveys that you have 20 chemical elements and so on. Unfortunately, there is no time for everything, okay? These are the lectures I'm giving next week in another school, which is School 4, Galaxy Formation, Milky Way, and Small Milky Way. Okay? So, we had stopped here. We were in the bulge. We saw there was this discontinuity clear in alpha Varana versus iron. And then we saw that the very old, the things we can give age for, which are the globular clusters, these old building blocks, they were there, and we saw that they were old and in the place where we think the old stars could be, and when the spheroidal bulge is there, buried in the middle of the bar, the thin disk, the thick disk, and so on. Everything that's going on in the busy area of the bulge. Now, the question is, so this is transparency for last lecture. Now, transparency, I shouldn't say transparency, because Eduardo told me when you say transparency, you show you are old, because you know, for the young people, we had transparencies. You put like this, it's transparent project, and I was like, okay, so slides. So the question is, are the globular clusters born here? And this is the part that's important, because although I didn't cover the fact that our galaxy was hit by several merger events, and therefore, in our galaxy, there are also accreted stars. And the same way that there are accreted stars, there are also accreted globular clusters. So when a galaxy comes and punch with our galaxy, it brings gas, it brings their own stars, and their globular clusters. And some survive, right? So it's not a given that if you find a globular cluster, it is born here. It could have been accreted. So there's a whole area on that too, open up because of Gaia, essentially. And so we need to do a small detour before we go back to what we want to say. The small detour is usually when I shouldn't talk about this, but it will help you to understand. So the first one thing we understood from this lecture is that we can enable a lot of science if we have large data sets for which we have 6D phase space information, which is position velocities, ND chemistry, so multidimensional chemistry, and age. So lots is going on in the halo, but this lecture does not talk about the halo. So I really invite you to read the review by Helmi 2020 and the reference that are in. And I give you a tip. We are in 2023. This area is a lot happening. So if you want to know what happened after the review, you see who is quoting that review, and through that you get all the literature that is work on that field. So that's a tip for the students. You know, you should do this for reviews that have some time already, some age. So browse the papers that quote that paper. So in this detour, I'm going to talk about the halo, but just the basics. So after Gaia DR2, we found the Gaia Enceladus. And I cannot finish talk about the galaxy without talking about Gaia Enceladus. So here, in the Helmi 2018, which came with Gaia DR2, you have in one side the simulation, one side the data. And this is a simulation where a galaxy collides with ours, a small galaxy. This is the famous Tumru diagram, which you have the velocities in direction x, z, and y. And this is here where you find the thin disk stars, usually in this parameter space. The thick disk stars are here. And you see a bunch of things here. And if you are to this side, they are retrograde orbits. So you have a bunch of retrograde orbits. No? And if you do simulation, she saw that, and the simulation showed that if you had a satellite that kicked in our galaxy and merged, you would have a production of, depending on the mass of the satellite, of the inclination of the satellite, you would have this excess of stars towards counter-rotating, but other things. You see an arm here, you have an arm here, there are many structures. And then another way to see this was seen almost at the same time without, not in this paper by Belokurov et al. 2018. If you just plot here the circular velocity and the radial motion of the star, so velocity, and the galactic disk is here, so it's around 200 kilometers per second in velocity without too much excursion in the radial direction. But then you see this extra thing here. This is the Gaia Enceladus again. In the velocity space, you see it very clear. And Belokurov called this the sausage. That's why they both discovered at the same time. So now we have to speak about this as the Gaia Enceladus sausage. Okay? Because this way both are into, because they discovered at the same time. So the local halo is dominated by this retrograde population reminiscent of an impact with Gaia Enceladus around 10 gigayears ago. Similar to simulation of a large impact with the Milky Way, where the mass ratio is 20% that the Milky Way had at that time. How we know that was 10 gigayears ago, I will show you in a while. Lots of activities are in the field, because in this field you are combining then Gaia, so the velocities, astroseismology if you have, spectroscopy, and then you have this booming literature here, that I put here for you, and there are more, but papers that are only looking to the halo and all this that you can find, because Gaia Enceladus is not the only thing that's there. So if you have distance, radial velocity, chemistry, and age, you are in the game to do that. So we had, for SEGWE, as I said, SEGWE was a spectroscopic survey that has very low resolution but large wavelength coverage. And when we run StarHorse over all the spectroscope surveys, as I show you, the Queiroz et al. 2023, we could get for close-by stars, if they were subgiants, ages as well. And I saw that alpha Verana versus iron, there was a lot of old stars at low alpha. So old stars should be usually high alpha, okay? Unless they are debris that was forming very slowly, as we studied before, and therefore this old low alpha means I have in that data set accreted stars, for sure. And why in SEGWE? Because SEGWE went deep, and so you can see better this population than the other surveys that were more shallow. So even though the spectroscopic results were not so good, it was a good sample to check, because now I had a good distance, good velocities, because that radial velocity is easy to measure, and the chemistry was so-and-so, but I could check who is the suspect of being an old low alpha at low metallicity, where the halo will be high alpha, low metallicity. So you have this excess of stars. So I asked Guilherme to have a look in this data. This is the data, the StarHorse, before we publish, right? Also as a validation check for our ages, our data. And here is the distribution of this data set, SEGWE per StarHorse at low metallicity, so selecting only the low metallicity, because SEGWE had also a bias towards low metallicity, it has more low metallicity than Apogee, so it was the one to check this. You see, for each survey, that's the question I have, the scientific question. So SEGWE was perfect for that. And this is the distribution X and Y, so the SEGWE is sitting here more or less at the solar vicinity, but as I said, go deeper, and has a lot of stars in the thick disk, okay? So we computed the angular momentum, which is in relation with the velocities at the different directions, we have them, and then we computed what we call the actions. These are conserved quantities in kinematics, and then, for example, the J, this action in the direction phi, is essentially the angular momentum in the z direction. So this is explained how to do. This is something that's done for all papers that are using these things. So let's see what has happened. So here, if I use there is a way to select things that are punching the Milky Way, as you saw, either in radially orbits or vertical orbits, the mergers. And so you can you can take the data and plot them here in angular momentum in the y direction and in the z direction, or energy versus one of the LZ direction, or one JZ versus JF, and there you can play, okay? The important thing is that if I choose this parameter space here, I will have predominantly radial orbits. I will see Gaia Enceladus, which is here. It's pumping up here. But he had the idea to look to the predominantly polar orbits. And when I look to predominant polar orbits, I find the other debris that are predominantly still in polar orbits. For example, here, there is this overdensity clear in this. And these are good candidates for Sagittarius. You see? So in 2 seconds, we increased in 2 seconds now, but using that data file that was not even published, we increased the number of star candidates in Sagittarius by a lot. And for a couple of those, we have also the Sagittarius collide with our galaxy. The nucleus is there behind the bulge, but there is the trailing arms. While it was colliding with the galaxy, you can watch the movies that are around, you have arms of debris that are forming. And we have, with this, some arms pass here nearby. So we could have samples like extended sample where we reach Sagittarius far away, with the trailing arm passing here. Oops, some of the stars are subgiants. So I can date the trailing arms, you see? So we didn't think about all that before, but I saw a data file that has a potential to give something, and then you go there and data mine it. So here you see that these are our selection for Sagittarius. We concentrated here. And that you have other things, Cetus, Helmstream, Orphan, Vulcan, and then you have a whole family of these accreted other objects that you can now select based on this kind of kinematic, angular momentum, and action space, and then go study their chemistry, their age, and then get the chemical evolution history of each of the building blocks of the Milky Way, which is also, that's why there's so many people doing. So using this data set and the Star Wars distance and Gaia, the selection immediately doubles the number of the non-Sagittarius member at low metallicity at the moment we are publishing. We have 1,600 string members, including more than 200 very metal poor stars, which means stars that are below -2 in metallicity, no? And 7 globular clusters. And we find that the leading arm, so the arm that's more close to us, is metal poor, is more metal poor by 0.2 dex and older with respect to the trailing arm. So that could translate to the idea that the galaxy, Sagittarius, before colliding with us, had even a gradient, an abundance gradient. I find this really amazing, you know. We are able to find the galaxy falling to ours. We are able to study in detail the stars in this galaxy. So as the galaxy is far away, a dwarf galaxy, to have this level of information, I have to go to integrated spectra or to go to a ELT. But the stars are brought here to my backyard, and I'm just having to find them and study them. So I find this really nice. It's a kind of data set. So the data set's public. You can go there and data mine the rest, you know. And so here then we have compares of the metallicity distributions that we have for the different, and we could compare our full sample with also with age for those that we had age. This is the position of the sun. This is one of the globular clusters. This is how the model predicts the trailing arm and the leading arm is going, and so on, the distribution on the space. But I can never just, find the arms easily on the space because they are mixed with other stars. I have to go to the kinematic diagrams I showed you before, and we can find. So this is an example of this many science we can do. As I said, we got 200 very metal poor stars. And we provide also the first age estimates for individual stars in the Sagittarius stream. There were not before in the literature. With a subsample of only 56 turn-off and subgiant stars, and we find a median age of 11.7 giga-year. Because now I'm in the subgiant branch, I can use a little bit isochron age, right? And this is similar to the thick disk. and so on and so off. So we can also find, if I do the alpha over iron versus iron for this data set, here is the full sample. This is my leading iron, trailing iron. I can compare how the alpha over iron versus iron goes for the trailing iron and the leading iron, very similar. And I also, of course, have in this data set Guy Enceladus, which dominates the thing. And I can compare with Guy Enceladus. I see that the Sagittarius stream has lower alphas than the Guy Enceladus, that has lower alpha over iron than the in situ population here. And this gives me an idea of star formation histories. Okay? So this is, I think, something that can happen a lot. End of the tour, okay? So having this in mind, that we can do this, and that there are things falling in our galaxy and the stars that are created, and I can find them. Now, when you go to the bulge, it's not so easy. And that's what I want to say. So this is the same energy angular momentum plot. Everything I show you, we're here up. But when you are at these lower energies here, which means too much phase space mixed already. It lost information mostly. And now how you tell if the blobs that are here is the main situ bulge, or is some people found this thing that is called Heracles, and that is in principle something that is a debris that is found there inside the bulge. There are difficulties here. So to disentangle in this diagram, forget it. Okay? So our globular clusters are sitting here. So the globular clusters we have been discussing before in the bulge, are they in situ or are they accreted? Don't know, right? So we need what to give the answer? Chemistry and age, because that's going to give us the answer. So I show you this plot. Before, remember our little stars were here. They seem to be following this is the main population of high alphas. They seem to be in line with the main population, but depends on the chemical elements. So they seem to be in line. But then we can resort to other chemical elements, and this is a classical thing, the way that people are also using a lot for the halo. If I plot all the data set from Apogee, for example, DR14, I have the thin disk, I have the thick disk, and I seem to have an extension here, blob. Turns out this is Guy Enceladus. Okay? It's a bit lower alpha is metal poor. But if I plot in carbon plus nitrogen divided iron first iron, the blob goes farther away of the main galaxy body. So if I have another chemical element that do this job, then it gets easier. If I go to aluminium, look where the blob is. If then I will combine more, I will do magnesium over manganese, aluminium over iron. Look the blob. And look two blobs here, thin and thick disk. Okay? So I don't have to be sitting with the half over iron if I have other things. But I not always have other things. But here, this sort of diagram became very useful. This is what people say. Magnesium over manganese versus aluminum over iron. Here is a locus for normally ex situ stars, and this is more a locus for in situ stars. But nature, as I said, there is always a but, and this is the but. For the globular clusters, our globular cluster is sitting here in the in situ, but there is this one that depending on which population, because the globular clusters turn out to not be a single stellar population as people used to think. There is a multiple population. There is the primordial population, the secondary population. And for some elements, the globular clusters change the abundances. And this globular cluster is playing with us because we want to say, is this globular cluster in Syrah? It stay there. Why here in the middle? Because some stars of the second generation are here, some stars of the first generation are there. So then what can you do? So you saw the chemistry already helped you, but it was not enough. Then you can do good age, because for the globular cluster you have good ages. Now I plot iron versus age, and here I have from this paper here a lot of accreted globular clusters. And this is the age-metallist relation of these accreted globular clusters. The really old building blocks, this curve is almost like the one of the toy model I show you for forming the bulge. Pump up star formation history that pump up iron in half a gigayear. And look where the globular clusters are. This one is here. Yeah, but the error bar, the error bar is a pain. It's going there, but still, okay? This is coming from, the ages come from a CMD, from HST data. Okay, so you need the HST data, the good chemistry, you need everything, and then you can do this. I find this paper very beautiful. It's from a Brazilian student, Souza et al., 2023, and I invite you to have a look. Okay, so we are here fighting all these lectures to find the pristine building blocks in the bulge. Okay, now if I go to high redshift galaxies, what do I see now with this fantastic data? I start seeing what is becoming very common, these clumps at high redshift. These are clumps of high star formation history at high redshift. And there is an idea that an early thick disk and an early bulge, these clumps could coalesce in the very high redshift and migrate to the inner part very quickly. So all the building blocks, because this is very high redshift, all the building blocks could be where? There, in the center of the galaxy, in the inner 1 and 2 kiloparsec. And that's where we think we are seeing the oldest population in the Milky Way. We are talking about, as I said, we are redshift 5 when we are back to this age of the pristine building blocks, globular clusters we have in the Milky Way. So there is a lot happening here to try to explain the old bulge and relate these to high redshift clumps. There are models and so on. So the question is, where are the local counterparts of star formation clumps that we see at high redshift? If our galaxies, as many are looking now to the galaxy but not doing the job we're doing, just think it's a thin disk and a thick disk is not old enough to get the thick disk has an age that's also similar to this old bulge. Now we constrain it from the solar vicinity. I show you in lecture 2 is 11 gigayears. And the globular cluster is a bit older than 11 gigayears. So a lot is happening in the first 1-2 gigayears. Okay? So this is interesting. Now, I wanted to just dive now to another thing, that with big surveys and good chemistry, start finding rare stuff. Most of what I say is the general. Low alpha, and then you plot very good data and you find a star here. This is magnesium over iron versus iron. So what is this star doing here, right? And so this you can still explain, but it's at metallicity minus 2.5. It's a very metal poor star. It's extremely metal poor star with very low alpha. And now it starts being difficult, because I can explain low alpha if I gave time for the galaxy to go, like Magellanic Clouds and Sagittarius, but minus 2.5 start to be complicated. It turns out that this is a metal poor star with abundance that have characteristics of a pair instability supernova. That was not found yet. So this is why I think it was a Nature article here from the people. And then they study all the chemistry of these stars compared to models and see that this looks like a fossil record of explosion of a pair-stability supernova that didn't left any core, anything, and this would be an explosion of a very massive star. Okay? But there are other weirdos. Now we have statistics and we have weirdos. Most of the talk that I gave, we are here. This is apogee. But suddenly we have all these people here in nitrogen. They are orders of magnitude above. And if I compare with Sagittarius, LMC, SMC, they are not. They are all here. And so these are the contours for the others. So you cannot explain them as accretion. There is something that is making this very high nitrogen. And what we discover, so we cannot explain this with dwarf galaxies accretion. We need to explain this with debris of globular clusters. So the globular clusters not only have two populations, but lose stars everywhere, and these are mixed in the bulge, especially in the bulge. And now you have debris of globular clusters, and they show high nitrogen. So, and you have a whole plethora. We found nitrogen rich, aluminum rich, silicon rich, phosphor rich, strange things with sodium rich, and so on. And now you have a lot of explain. So, for example, people discovered this very high phosphorus. This is a sample of apogee here. This is the normal data, and this is these weird stars. And now they found that these stars correlate with high silicon. There is no way to explain that. Okay, here, another one. This is oxygen, magnesium, aluminum, silicon, calcium, and nickel. Look where for example, silicon is. I mean, the plateau is here. What is going on here? It is a burst with stuff with a top-heavy IMF, because that's the way I have to place only massive stars died and increase my silicon for a lot, but then they have to all be very massive because the massive stars have the stellar yields here. How can I go there? At the beginning I saw this, I said, oh, wrong abundance. But it's not. People have been there sitting and look. They looked first in this, but then they found in other, and then in other elements they are just normal. So these are happening a lot. So the main challenges now are, we have many more statistically significant rare samples. And for these rare samples we have age, velocity, position, and also they are coming from where? From not only because we increased the statistics, but because we went to regions that were first hidden to us. These are apogee data. We didn't, as I showed you in the beginning, we are punching the bulge. We are getting to a region that we were not there yet. And now we are seeing weirdos, and we have to explain them. Not everything can be accreted objects. Not everything can be debris of globular cluster. So the theory has to go on. So we need for new and more stronger stellar model beyond standard models, stellar models. So we think stellar evolution is done. It's not. The Milky Way is showing you stellar evolution is not done. We are able to test not only the stellar yields, but the dependence with other parameters. We can test time scales. There are maybe different types of type 1a supernova. This is something that's really happening also now. And also we need to be able to extract a good abundance for huge data sets, because the data sets here are huge and are going to be larger. So we are seeing stars born far away that are now here. We are seeing accreted stars. It's a mess, okay? So we need investments, and now I'm coming to a point. We need investment in stellar evolution theory, okay? The stellar evolution theory, not only to explain the weirdos, but these are the backbone of all the models of galaxy are sitting on, if you want to use for integrated spectra and so on. Okay, so where's next? So I finished the bulge, say bye to the bulge, but now where's next? In 2000, when was this? 2008, when I was still a person without a kid. In 2008, we wrote this thing here, which was an ESA-ESO working group on galaxy populations, a book you can download from the internet, where we are discussing up to where we had arrived in 2008 and what we need to be thinking already to complement Gaia when Gaia would come up, okay? And when Gaia came up, the first thing it was found was Gaia Enceladus, which I just told you. So we have all these papers and so on. So we have to explore the synergies with Gaia and other sciences here. This was our goal. And that's when was born the foremost, the weave, and the moons, more or less. So you need these strategic documents to discuss this, where we go, right? But the discoveries of Gaia, as I showed you, still in the beginning, and we are in the beginning, are focused on the nearby. Imagine what can we discover when we extend this to good parallax from data release 4 and 5. We will extend the map in the galaxy with very good parallax. So we can go very far away. So the goal here of the community of Gaia Galactic Archaeology now is to expand the Gaia legacy. And we are doing this by constructing multi-object spectrograph with large field of view, because I need a lot of stars, okay? And so I will complement then Gaia with chemistry, radio velocities, and we need a very efficient way to design the target selection of our surveys. All the surveys I told you before didn't have Gaia when they prepared the surveys. Now we can be clever, and we have Gaia, so we can prepare the survey in a bit different way, and this was a very good exercise of thinking. Gaia will give me the positions, the translational velocity via the proper motion, and for some bright stars, the radial velocity, for the RVS stars. The rest will have been done by foremost, weave, Sloan 5, and foremost and weave are in different hemisphere. We discussed some of the questions in this Drª Chiappini et al. 2017 paper, how to prepare for this. So let me give you an idea of timescale. We are here in 2024, and I'm going to go in this slide up to 2030. Compute your age. Because when you get here and you are like 40, 45, or even before, you are going to be the one driving what's going to be next. It's not going to happen naturally. You are driving. So you better engage. if you like this subject. So this here is taking spectroscopic surveys to a different level, because it's a massive spectroscopic survey, multi-object at wide field. So we're talking about some stuff with 2,000 fibers. So the apogee was like 300 fibers. We are talking now about 2,000 fibers. So we went for few hundred fibers to few thousand fibers. And this is happening now. Sloan 5 is already happening. WIV is installed, but I don't know exactly what's the status. We are starting, Formos is starting next year. I was the project science of the whole Formos project. I was galactic and extragalactic until we passed the competition with moons. In the end, we kill ourselves and both are going on. That's great. And then I am not the project science anymore since 2014. I am the PI of the disk and bulge low resolution survey to cover all the bulge and disk. And then 24, 5, 6, 7, here we are in the end of Foremost. We will have all this data, and there it comes the ELT first light. And here we have Mosaic and Andes. These are multi-object spectrograph, but now the field is narrower, but you are in a ELT. And what I'm going to observe with LT? Oh, you better find very interesting thing here. This is the time to find what you need to follow up here. You see? So, more or less. So this is, you're going to find a lot of things here, and that go to 35 here. Now, I'm focusing on European leading projects, okay? So here, the seismology. We had Corot, Kepler, K2, and TESS, all happening just at the same time of the other surveys. Now we have this done. And now we are starting the surveys. Of course, the spectroscopic surveys will have to follow up the seismic targets. We cannot go on without them. And this is a huge discussion because, oh yeah, but your field of K2 is not efficient for the extragalactic survey. Fine, but we have to go there. You know, so we have to find a deal, because I'm not going to do galactic archaeology in 2024 without my targets with seismic. I wish I had a seismic all over, or I don't have, so at least those I need to have, because they are hanging. They are my anchors, you know, my anchors in distance, my anchors in age, my anchors of the whole thing of million targets that will come. So I'm not going without them. And all of them are also following up this. Okay, so that's why I put it here. And then there is Plato. Plato is starting 2026. A seismic mission approved. ESA is going to fly now, soon, doing planets. But we will have a little bit of giants after a lot of discussion. And unfortunately, few. Okay? Unfortunately. Let's see what's going to happen. But Plato would give me seismology in large field. Pixel size not so good to go to crowded areas. But still, you could get ages somewhere else. Okay, and then you have Gaia. Same thing is happening here. Gaia, we are here, Gaia DR3, we got a bit of RVS. Then we're going to have a lot of RVS in Gaia DR4. That's happening not before the end of 25. And then we have Gaia DR5. By the time I have Gaia DR5, I have a stupendous parallax, proper motion. And I have, look what happened. I have this, I have done all this, I have discovered a lot of things. I am doing the job. So I really wish I had another 20 years of job here before retiring. So here I see as a phase of huge discovery space. This was a phase of huge discovery space, as I show you. This is illustrated by also the 2010-2020 surveys. And now we are complementing this also in the near-infrared more. And this is a phase of increased volume with high precision data in huge follow-up discovery of rare objects. That's how I see this phase. So here, multiplex of hundreds to thousand, and then something is appearing here in the end. Look, WST is a new project of a large mirror telescope that we are discussing with many fibers, from few thousands to like 10,000, whatever. Multiplex going to 10,000 to 20,000. So what has to happen here in this way? We have to be able to extract stellar parameters from huge data sets. We have to be able to reach precision of chemistry, radial velocity, huge data sets, covering the whole HR diagram. We have to. So we need what? Machine learning, because nobody's going to be there. Oh, here the the line. I mean, only for the tip of the iceberg that you are finding, and always you need spectroscopies. You need to not get rid of your spectroscopies that do individual spectroscopy, because all the machine learned things, they need training sets. And if you do not have a good training sample, forget about your results of machine learning. So you see, we are already risking two things: that we lose expertise in stellar evolution, and that we lose expertise in spectroscopy in a moment that we cannot lose. Okay, and then you had also from ESA, Hading, and Gaian infrared. So why? Because at the same time all this is happening, the ESA put out this Voyage 2050, which is a call for proposals for middle-size missions, and only 5 missions were chosen after a lot of this, and one of the missions was supposed to design, to carry out pure astroseismology, to characterize stars in a wide range of stellar environments, and would provide key information on stellar physics, and would allow testing of stellar evolution models. Testing of stellar evolution models with astroseismology in clusters. Because seismology right now has big pixel, Plato, Corot, they cannot do clusters. And the clusters, in open clusters, for example, you have a hold. So you can test stellar evolution there. So that's how we designed Hading. There's a paper in 2021. Hading, who died yesterday, is high precision astroseismology in dense fields. And what was the key point of Hading? These are the missions of seismology: Corot, TESS, Kepler, Plato, Hading. Look at the PSF, 1.3 arc seconds. So if you are looking at an image like this, you are looking like this with TESS, with Plato, with Kepler. This is Hading. I can go to a cluster, I can go to the bulge. No, I could. Cannot go anymore. So it was very fast. We had a ESA call for proposal in December 21, and they said, "Oh, are you not busy there?" Yeah, but the call was 2021, and they need an answer already a few months later, and they are selecting already in November 22. So this is the kind of thing: you leave everything and you rush to do things in a group that can do that. And then we were selected in November 22. And then it was a desperation, because we had to do these 8 sections of concurrent design facility survey, pass these reports. All this is happening in a very short time scale. And then we had the review, we passed this review, but then we had to be selected. This happened yesterday, and we were not selected. From the 5, we were not selected. Here are we. We are here in the ESA. This is the ESA technique people, because before you get to that age, you have to design the spaceship perfectly. You have all the requirements. It's not like an idea, I'm going to do like this. No. All the details were decided. So we had to 8 sections with all the technicals of the ESA. All of us online. Dejuque Cavata here, Andrea Emilio here. And enjoy the process. You know, it was a good experience, and we didn't. But is everything ready? And if there is another M call, we are there. Why dense fields? Why did we need to do that? Well, because they will be benchmark for calibration of absolute age scale is missing. We have only relative age scale. They would be benchmark for calibration of the cosmic distance scale and formation history of the building blocks. And there was one field in the bulge which would give me 70,000 stars with precise age seismology. Forget about. Okay, now this was the answer from yesterday. We're not going, but we have still something else. Of course, you always have something else. Not to get depressed. This is Gaian infrared. Here is the simulation of the density in objects that you would see per square degree in Gaian infrared. You would see a lot of stars in the region of the disk and the bulge. And this is in a paper also that we wrote to also 2021 call. And this is a plot showing the ratio between the number density of Gaian infrared and the expected number density of Gaia. So that's showing you that you have a factor between 6 or 8 or 10 more targets than Gaia in these regions that are red. Okay? But this is science by itself, because we are not even sure that this is the factor. This is a model. So this is what you have. You would do a lot here, and you would do normal Gaia here, because you would do 20 years after. So the DR5 parallax will get even better, and proper motion especially, by really a factor of 6, I think. So with that we can probe the hidden regions of the Milky Way, improve the proper motions of the Gaia stars that we have right now in DR5, and reset the optical reference frame, which is a very important thing also in Gaia, and extend to infrared. And this here plays a key role again, the bulge, right? And we expect to have, instead of 1.7 billion stars, we're going to have at least 8 billion stars. So be prepared for your machine learning. Now computer age. This is not happening before 2050. Okay. If I show you, if you run Star Horse over Gaia EDR3, and we have the just what we have Gaia, even for the ones that have Gaia in this region, we have a bad, this is Star Horse, the percentage of okay results is reduced a lot. Star Horse cannot converge, means parallax very bad, nothing is working anymore. So even for those that are in the inner galaxy, there are issues. And we see this in this kind of plot. So you really need another Gaia. What's the time scale here? 2010 initial proposal, we could not go. They did CDF, didn't pass. Same thing. Now we are on the ball again. Concept and development of the proposal phase. Here we are working like crazy. And then 2030 design. If we pass, if we are accepted, launch after 2040. So Gaia infrared, all sky astrometry and photometry to penetrate the obscure regions and to observe intrinsically red objects with almost diffraction limit resolution. Bulging inner disk, that's what we are doing here. Improved proper motions with 14 times smaller errors than from Gaia alone, opening up a new science case, such as long period exoplanets and accurate halo measurements, far away. And also allow to slowly degrading because there will be a degrading the accuracy of the Gaia reference frame, and this will be reset by the time we have Gaia infrared. The explanation of everything of this is in this paper, 2021. Okay, so I have to get back to my scale. I always do this to see how old I will be, and then starting exercise, to be sure I'll be there. So what happens from now to 2040? And Hating was the perfect time, and I'm going to show you, we are not going to have this, but it's important to understand where we were. 2023, our Hating phase A would start. Phase 0 start, sorry. Then you have this Gaia DR3, we just got one in October, that's a focus release. Also, they have another thing happening in this slide. You have the huge multi-epoch large spatial resolution photometric surveys. The Vera Rubin, LSST, and the Nancy Roman photometry. And then you have the huge spectroscopic surveys pushing, instead of the fields, we are going to areas. This is for most weave, so we are going to high areas of coverage. And this is for most weave and for most weaver end. And again, the data, the Gaia now in perspective to the photometric surveys. This is the WST I was talking about, a wide field 12 meter. We don't know if it will be funded. And here we are at the stage, we are selecting regions and individual targets for follow-up with ELT, which is now here, from here on, you see, ELT mosaic harmony, where we can now get ages. We don't need this, well, not that we don't need, but we are not going to cry much, but because we can still now do aids, isochron aids, at the subgiant level at the bulge, if I have this kind of instrument with this kind of precision of Gaia DR5. So I will be pushing to main sequence turn-off spectroscopy and in the need for precise age far away. And that's what we're going to do. But we don't have that. And then we miss to do this opportunity here, because Hating would give you precise age in the bulge, but will also, using the the clusters here nearby, would increase a lot the precision of the stellar models itself. So by the time you are here, and you have your main sequence turned off and the bulge where you use a time of telescope, very big telescopes and amazing LT, and you do not have good stellar models, what about your ages? In a region that's complicated, in a region that you have to figure out who is an 8 gigayear, who is a 13. That's the kind of precision we need. So that's why I'm sad. Because even though we are going to get AIDS, we are going to miss this piece here. Unless there is another call and we are still there. Okay, so in the meantime we have foremost with Moon's Sloan. This will open then interesting regions to focus for future ELT. Where to focus, you have to figure out. How to connect with the properties now of our galaxy with nearby galaxies. This is a field that's opening a lot because Muse, instruments like Muse with very good spatial resolution will give you a lot of information, and you now can combine both. And the chemical evolution models, the chemical evolution model community will have to catch up with the new data. And that's what we discussed in another group yesterday, because we are not going to pass a line over data anymore, because you have information of multi-populations debris in this data, so you cannot just do chemical evolution as the old way. Okay, how much time I have? Okay, so because I'm PI of this, I have to talk about this. I want to give you an idea. So this is a foremost spectrograph being built in my institute, which is the PI Institute, but we have a consortium with several institutes. And this is a spectrograph that's going to be put in the VISTA telescope. The other instruments that were in VISTA telescope were taken out already, because we are going to be installing that. It should be now, but there were some issues and whatever, as usual. But we are going to install the foremost here. Pieces of foremost are just next door to my office, so every day there is a piece going away, and I see there my low resolution spectrograph. So this is the galaxy map I have shown you, and this is where we are with foremost. You see there is a lack of data in this azimuth, in the bulge, and so on. Foremost is optical, so I'm not going to the bulge like this. I'm going above, I'm going where the optical can go. But still, we'll complement the windows I show you at high galactic latitudes. And so this is where the other surveys are, and this is where we are complementing. In the north, it will be with. We are doing the southern hemisphere, so we are complementing here. Of course, this is not a simple job, so we have the group in my survey is really huge. I am PI with co-PI Ivan Minchev, and this is more or less our catalogs. We have here in the sun. We will have an extended solar vicinity sample, because there the Gaia data will be like the data. You can obtain exquisite age, everything you want. Then you have an extended cover of the disk, which is called dynamical disk and chemical disk. The two things are the same footprint, but for the dynamic disk we request less signal to noise, so that we do a lot of dynamics. That's why it's called dynamics. And then for the same but very dense, a lot of data. And for a more less dense sample, but on the same footprint, we request more signal to noise to do chemistry, and that's what we call chemical disk. Okay. And then you have the big. The big is the bulge inner galaxy sample. And inside the big, you have the bulge deep. Because I am not going not to do the bulge with this. So currently we are like 66 members in my survey. This keep entering and going out. There are several rules for that. Because projects are made of people, so people that are putting their time in the survey. The survey has been a growing story because of Gaia. So because we need to be able to choose the best targets. From the 1.8 billion, I have to choose only 10 million, because I have a budget in fiber hours, and I have a budget of time, and I have to share the time with people who don't want to be in the galactic plane, which are a lot. So, but we can also use the Star Horse to select, because Star Horse to select the targets is a model-dependent thing. We have to select based on observables, otherwise we have bias. This is a very important thing in galactic, because we cannot have bias in these samples. But we can then use Star Horse to check if our selection is working. That's what we are doing. So in Gaia DR2, we had already run the first Star Horse set. So that's why we developed Star Horse as well. Okay, to take advantage of the data, but at the same time, applying already to what we had to prepare, because we had to prepare more catalogs. And so there is a description of our survey in the Messenger of ISO in 2019. Essentially, where we describe a little bit how to select the best 10 million from 1.8 million, and this is how we think we should select. We cannot just go and observe like this. We have these catalogs tailored for that. That's how we build this. And then you need the seismic giant catalogs, the clusters catalog. These are our anchors. and we have very good people here taking care of this sub-survey, as I call. Clusters, we need a minimum set of clusters to really also hold on. And then we're going to have the very metal poor stars and the bulge deep. So this is going along the way. So then we had the apogee, Sloan, and then here we did a proof of concept, and this is our paper of 2020. At the same time, it was the PhD of Anna. I wanted to check if Star Wars plus photometry plus is giving me good distance, and if we are going to be able to do the job. And then we had the proposal, official proposal to ISO in the end of 2020. We have to write the big proposal for the large programs. And then I add here the ancillary science. Because in the footprint, you can do ancillary science. If I'm sitting there, you have a fantastic example of something, we can do also. And that was, our GTO proposal was in the end of 2020. Ancillary science, we have Cepheids, planetary nebula, white dwarfs, hot subdwarfs, very metal poor stars, for which you have coming from the PIG survey, which is a survey that have candidates metal poor by observing with narrow filters. And then the white dwarfs in compacted white dwarfs and a sample of 100 parsec white dwarfs. Then we had Gaia EDR3, and now we could do something that was very important for our survey, that was extinction filtering. Because I have a final budget of fiber hours, I cannot go to too high extinction regions, because then I request a signal to noise and I lose all my fiber hours there. But well, the disk has extinction, so I have to go up to a certain place. So I need to know how to filter that, and for that I need to wait Gaia EDR3, because with that Gaia EDR3 getting better, the photometry plus Gaia that is in Anders et al. Paper 2022 was better. And then I could get trust more the extinctions and could then use that to filter where I don't want to go. But this is not a problem. So we filtered that, and then we had another after DR17 in Apogee. We had also proof of concept to show that we could go to the bulge and that we could also estimate ages. So this is the paper KROS 21 and KROS 23 that I discussed here in these lectures. Then something happened. Community survey joined, because we had to leave some stuff for the community surveys to join, because it's ISO, you know. So we have the consortium survey, people are putting money, but it has to be open to community. So community surveys sent their projects, and they were selected. And there was a one call to enter foremost. And then they joined. And then we had Gaia DR3, that's why we don't have peace. And then we are now in the phase of optimization. What does it mean? I have to worry about cadence, how I'm going to do the very metal poor candidates using Gaia to find them, and then optimize the bulge deep, and that's what we are doing right now. And then, we also had then entering OB stars entering here to complement the weave, and now hopefully we will be on the sky doing all this. I don't know how and how it will be my life, but we will do. And let's just finish showing you how we do that. We select without using Star Horse. We go there and select. In each beam, in a direction, in a cone, we use the parallax distribution, the PDFs of the parallax, to make such that I don't have all the stars falling here. That I have enough targets at each hue pixel, enough targets far away, because I don't want to be doing the same surveys that we are doing since 10 and 20 years. I want to go expand, right? So I do this, I select those targets, but then I have to see what I'm selecting. And I then look to what Star Horse has for that selection. For example, I selected the dim, I do not use the Star Horse, but I plotted the CMD that Star Horse will give me by corrector extinction. And then I filter that, because I see the extinction of Star Horse, I see where I cannot go, because EB minus V get too high, I don't get my signal to noise, I cut it out, I mask this, and then I am left with, for example, these are throwaway, and then I get 4 million targets for example, this dim catalog, from which only 2 million will be observed. I can do this for CAM, you see it's the same, but CAM now, here is larger, the cut, because I need more signal to noise, so forget about going to high extinction. I need to go away, and I test this. Well, once I have this, I test with Star Horse, because, I mean, can you imagine, we are not in the sky and I have this plot. Crazy. This plot is what? Epsilon x of the galaxy, the distribution of my targets in X and Y, and then in Z, higher from the plane, Z and R here. So for example, the dim survey, I check then that there is a simulator that observe, giving all the constraints of all the other surveys, and then I see, okay, not observed 24% of our sample, observed but failed, meaning observed but didn't reach the signal to noise. I see where they are, and I see successful. In this case, 70% almost of the sample successful. The dim catalog is really extending. This is the sun. This is the radio distribution. I will have a hole here into the bulge. And then I can complement the bulge. I go into a box here. I ask the big catalog. In the big catalog, I have another footprint. Here is the bulge deep. Here is the Sagittarius. It's a community survey. And on top of this, I have the peak survey, very metal poor candidates in the bulge that had photometry to select good candidates. And another important thing of this survey, I'll finalize soon, is that the wavelength range is very extended. The resolution is okay, what we could get after many, here we are at 5 to 7,000. But we have these several lines, so we are exploring a lot machine learning approach to extract the good abundances from this spectrum, because we have the lines, and we are preparing test papers where we apply machine learning possibilities that we believe and want to test how good they do. And we are applying in these papers, Guillaume 2020, we apply to RAVE, here we apply to Gaia ISO, and here now we apply CNN to RVS. And there we see how good we can go even when we go low signal to noise. So we are doing all these at the same time to be able to be ready for what's coming. So definitively, we are not a radio velocity survey. We are a chemodynamic survey. Otherwise, if we don't get chemistry, I'm not a PI anymore. Then Ivan is there by himself. I hope we don't broadcast this. Okay, at the same time, in the bulge area, now here you are 35 degrees to, well, this big footprint here is like the big footprint. You have the BDBS, the DES footprint for the bulge of Mike Ridge, only photometry, but very good way to, it's more than 200 square degrees, photometry, this one, and they have 250 million stars. So the complementation with photometry is key, okay? And this is the Blanco DCAM bulge survey. This is a field in Sagittarius. These are control fields in what they call disk. And now we want to do the bulge inner disk, the very metal poor, as you saw, the peaks, the radial velocity and abundance in this region. This is the big. Look the area that we are getting, hopefully. So, yeah. And then here I'm just focusing in this area, small. And this is the area we are covering where the global clusters were that I was showing you. This is the bulge deep, where I'm going deep here. The southern bulge where there is less extinction. And I'm going to get more targets there. Okay, so that's the end of this lecture. And my main take point for all these lectures to you is this. The data is there. The questions are there. The challenge for this generation is to be able to combine expertise, to combine, understand and that means you don't need to know everything. You need to find a good collaborator. Like I did. I'm in a rush. I have a file. I want to check this file. I think there is Sagittarius there. Who? Guilherme. Why Guilherme? Because I had collaborated with him before, so he was like fast and interested, and that's his thing to catch these things. And he had his love for that, so give to him the file. And 2, 3, 4, Zoom, we are done, So this is, I'm not going to do everything. I'm going to be alert that, but to be alert and have this, that's cool, you need to be informed. And to be informed is the challenge. You need to be able to read a lot and make the summary of the situation and say, okay, come with a question like Simone, what is next? Why do you need more? And now, I hope these 4 lectures gave you a picture of why we need more. And why should I not want more? Why? Money is being spent in science. And so we are the ones who are driving where they are spending how. And we means also a lot of Brazilians. So far, we Brazilians are outside. Many of us, some very good fighters are here, but when I finished my PhD, there was no position. So you start being outside, and then the answer you cannot come back. Some could come back, some could not. So let's hope that in the future, Brazil is really, and is already taking part of many of these things. Now, there is other surveys I didn't talk about, but that's the goal. Be alert, combining photometry, spectroscopy, seismology, whatever. So if you get sad that they cut heading, which is very sad, I have to say, because it was the only way to have precise aids in the bulge. We don't have that. I'm pissed, yes, but we may have got an infrared, and then we'll continue. We have many things. So that's the tip. And this is a fantastic time. From now to 2050, I have a full view of what's possible to do. So thank you very much for the attention, the patience. Thank you.
Thank you very much, Cristina, for this very nice lecture. So questions?
Congrats, Christian, on the great talk, and condolences on hiding. And related to this great call for arms in the end. So one question is, when you got the first approval for hiding, for instance, the rest of the process is funded by ESA? No, it's just by love.
Yeah. So that's why at that point you're not gonna ask a postdoc to spend 100 times. No, you have to leave everything and do yourself. And this was a bit weird at this time, I have to say, because usually you have a selection for phase A, and phase A is funded. So I had, if we were funded, I had already from DLR, which is the Spatial Institute from Germany. To get to here, I had to write a proposal, and then what are the working packages we are working, and so on. I had funded 5 million euros for the next 10 years to just case study of phase A and hating. And that 10 million euros, no, 5 million euros just disappeared yesterday. But okay.
Oh my.
Yeah.
And related to this, Brazil, I mean, supposing we're not able to plan 30 years ahead, but at least 10, from these surveys that you showed, what in your opinion would be best to join? I mean, slow. I mean, we've been always working with slow. There is slow 5, but then there is weave and foremost.
Yeah. So to join foremost now, difficult. I think. I mean, if we were ISO, we were in foremost. To give you an example. And we were not. I mean, we had the opportunity to be part of ISO in Brazil, and that was a very missed opportunity. And I understand there were some concerns that if we put too much of our coins at ISO, we didn't. There was a concern that is like, I would never have this concern. We don't have enough people working on this thing, we're not make use. We are, in Brazil, a population young. We have a lot of students. I have to work there with 1-2 people that appear, and my PhD student was Brazilian, you know? We are young, we have a lot of people. If we have the universities that are not crashing like happened last 4 years, if this does not repeat anymore, that's the problem. If that repeats again, budget cut at 90% level, forget it. But so that's the problem here, that we keep on going and then something boom and take out the money and people get back to scratch. How did the people did their PhD in these years? It was very hard. Not even there was hard for doing PhD in the pandemic and so on. But we were in an institute that had the money to keep on going, right? And so these things cannot happen. So I think that was a big mistake. Maybe there is another way to get back. ELT, not having ELT with the knowledge we have here of spectroscopists in Brazil, is sad. But be part of the large telescopes, but be part of the photometric surveys, because that's going to be very important. So Brazil is in LSST, I think. LSST was avoiding the bulge, but now has reconsidered. I think I even have here the last footprint I got from the LSST, and they are reconsidering. I think it's this one, yeah. And they are designing this right now because this is the region where they have the green is where is good, okay, where you have many visits, and this is the recent footprint refinements that they are doing, and the bulges now. You see, the green is extending here. It was not like this before, and this is like 750 visits. That's a lot to do here, you know. And then you could have a photometric metallicities, and then you can then follow up whatever the populations are. You're not going to have the radial velocities. That's the problem. Right? So yeah, photometric because you have millions, and then join. You know, if you're having a big project, and so I'm not going to join this project because I'm a postdoc and I have a permanent position. I see this a lot. I'm not going to spend my time in the surveying, but it's not that. You can have a PI. I mean, I protect people. I'm not gonna give you a bunch of things that you're gonna see doing all that. I protect people. Give the person something that's already there he's working on, that's already with the interest, and the person can develop and meet. You network in this book. You meet people, you know. And then you have a postdoc easy after, and then hopefully you can come back to Brazil.
Chris.
So first of all, thank you for all these amazing lectures. It was really, really good to have this review of the literature, to see this perspective that we need to think about the projects and the instruments that will be ready in 2040, 2050. So it was really great. My question is actually about the globular cluster and the in situ versus accreted scenario that you showed us. And that particular globular cluster that has by the error bar, it could be accreted or formed in situ.
Yeah.
In this case, shouldn't we look just for the first generation, since the chemical evolution that caused it to go to the other part of the plot comes from the evolution of the globular cluster itself?
Yes. Yes.
Yes? Okay.
Correct.
Okay, thank you.
And let me apologize with you because I still want to see your poster. You have the poster, right?
Yeah, it's
And
still
I
up
have a
there.
second. I stopped there in the way to the bathroom, but I didn't see. I forgot this. Wait. It's true because the globular cluster has changed. So we think the first generation is the original one, where the change in abundance haven't happened yet, right? And,
Yeah, because you showed it in the next slide. You showed the age, and the age is more consistent with it being formed in situ.
Exactly.
But I would trust the chemistry more.
Yeah. That one is a border case, and that's very tough. Want to finish with my hug to you all. I forgot this. This is a picture in a general assembly of AAU where they had this exhibition. It's an exhibition of the 100 years of IAU that you can ask to put somewhere, and they send to you the exhibition. And these were the chemistry, the chemical elements you cannot see very well, but here you have iron, and they were hanging like this, and people said, go inside the chemical elements, and so we took that picture. So, obrigada for the invitation, really.
But we have time for another question. No? When you get the final answer for Gaia infrared?
The Gaia infrared is more complex, so it didn't fit in the M mission. It was more expensive. So the medium mission is a mission up to 550 million euros, and the Gaia infrared will need more, so it's not going to be an M. And then there is another thing. There is an issue about using infrared detectors that you can do what Gaia does, go like this and get back to the same star all the time. So there is some technological issues, and these are being looked at. And so that's why I don't know exactly what's going to happen. It's not discarded yet, but it's not clear. But we don't want it to go up before 2045, because we need the difference of at least 20 years between Gaia and end of mission and the next one, so that we have an improvement. Even if we would go, you say, why don't you do a copy of the Gaia? Because that would already improve a lot. But that's, to justify a copy of something for the general community is very difficult. So you always have to do something and something more. And that's why it's Gaia and infrared. That's not easy.
So, last question? No? So, Cristina, Rafaela, thank you so much for accepting our invitation, for the amazing lectures. Okay? And thank you all for coming for the CCE edition 25, and I hope to see you again next year, okay? Thank you.